Welcome everyone to the ZX seminar. And today we have Matthew Sutcliffe, who will be talking about smarter k-partitioning of ZX diagrams for improved quantum circuit simulation. So Matthew, please take it away.
Okay, thank you. Okay, we'll get started then. So this is based on a recent paper which is up on arXiv, which I'll come back to at the end, but this is the title. So as a quick overview, I'm going to cover briefly what classical simulation is and how we can use ZX for this. So if you've been to any of my talks before, this will be very familiar. So we start with a quantum circuit. We translate it into a ZX diagram, and we apply the rewriting rules to simplify this. This is kind of the nature of ZX, as everyone here will be familiar. And these are the rewriting rules, which you'll all know. So how this applies to classical simulation, then, if we have a circuit, we can plug the inputs and outputs with some bit string that we want to measure. And if it's a Clifford circuit, then it will just reduce to a number. And this will be the amplitude. The absolute square of this will be the probability that we get this particular output bit string given this particular input bit string. When we're dealing with the broader Clifford plus T gate set, then we don't end up with just a number. When we reduce with the rewriting rules, we end up with some reduced graph. And then we need to apply decompositions, stabilizer decompositions to reduce this into a bunch of Clifford graphs that we can reduce to scalars. So this is an example of a decomposition we could use. This is the BSS example. And there are better examples since this. The optimal one right now is called the CATS example, the CATS decomposition, and that's the one we'll be using in this paper. So how this works is every time for every set of XT gates, you can reduce that into a sum of Cliffords, and then in each of those terms, you have to reduce again. So there's this exponential growth. So the number of terms you end up with is 2 to the alpha t, where t is the initial t count and alpha is just based on your decomposition efficiency. So that's a very quick overview of how this works. And you can imagine, if you're very lucky, you might end up with a situation like this, where naively you'd think that this has, let's say alpha is 0.5 to keep the math simple, and the t count shows 26. Now we would expect 2 to the 13 terms to calculate. But actually, you can see that this is two disjointed subgraphs that aren't connected to each other. So an optimization we can make here is to treat these independently. So this one would be able to reduce in 2 to the 7, and this one in 2 to the 6, and then we just multiply the answers together, which will be roughly 2 to the 7 again. So we've managed to drastically reduce the number of calculations just by treating these disjointed parts separately. But these are quite unrealistic in practice. You're unlikely to find a graph that happens to reduce into, like, say, 2 big disjointed parts. But if it's close to doing so, then you can apply a cutting decomposition to induce this. So in this case, we've got 2 subgraphs labeled with these blobs with one edge between them. We can cut this edge, which means we'll double the number of terms we have to compute, but we can potentially halve the t count that we have to deal with. So while we could double the number of calculations, we can also square root it so it works out better overall. And in general, then, if we're making C cuts, so let's say there's C edges between them, so 3 in this case, then we'd make C cuts, and that would leave us with 2 to the C number of terms to compute. And there's some redundancy here that we can address and optimize for. So firstly, imagine if we have a big graph that we can separate with 4 cuts into 2, and each of those we can separate, and each of those we can separate. Then we end up with this big chain where we've managed to reduce the t count potentially by a factor of 8 if this is even. So we'll just say G is the largest t count among these, and that becomes the dominant term. So we've reduced the t count dramatically, but in doing so, we've increased the number of cuts we have to make, which means that now this term on the left becomes dominant. So any gains we would have earned, we've kind of lost by having to do so many cuts. So that's the other thing we need to try and optimize for. So if you look at a very simple example here, you can see that we would end up with, in this case, we have 9 cuts. So we'd end up with 2 to the 9 terms, and these are the first 3 of those terms. And so for each one, when we're calculating, we are dealing with 4 independent ZX diagrams that we need to reduce. And that reducing process can be quite slow depending on the t counts they have. But you can maybe already see the first optimization, which is that in this first term, we're calculating C with all these zero inputs, D with all the zero inputs, and so on. And the next term is almost identical, except E and F have changed. They have this new pi parameter. But there's no sense in recalculating C with all the zeros and D with all the zeros because we've already calculated that. So what we do instead is calculate all the unique possible terms that each of these subgraphs can have. And then whenever we come back to something we've calculated before, we can just recall it from memory without having to recalculate it. So to put this into more formalized terms, if we look at an even simpler example, we can write this the sum of terms with parameters like this. And here we have 6 parameters, so there'll be 2 to the 6 terms in this summation for 64 terms overall. But actually, we can see that A only has 4 unique terms because there's only 2 parameters involved. And B only has 16 unique terms because there's only 4 parameters involved in B, and so on. So if we only calculate the unique terms, then we're actually only calculating, in this case, 36 ZX reductions rather than 64. And this is a very modest example. You can imagine on much larger scales, this would be the difference of magnitudes. But we still have to cross-reference these 64 times, right? We still have a sum with 64 sum and terms in it. It's just that each of those calculations now is much quicker because we don't have to repeat all the ZX work. And another thing we can do is make use of some work that Alex and I did last year or the year before, where we used GPU processing to try and calculate similar graphs in parallel on the GPU. So for instance, this A with the 2 parameters, the 4 possible states that can be, we can calculate that in a parallelized fashion on the GPU. So that's something else we can do, which will give us a big linear speedup, as we found. Okay, and then the next step is pairwise regrouping. So you can imagine in this case, where we have 2 to the 9 calculations to cross-reference all these together, so that the sum would give us 2 to the 9 because we have the 9 parameters. But instead, if we just imagine we don't want to regroup all of these subgraphs together, we'll just do it pairwise. So we want to group C and D together. Well, C and D only depend on 6 of these parameters. So within 6 calculations, we can regroup C and D into one subgraph. And then in 2 to the 6 calculations, we can do the same for C to the E and F. And then we only have 3 parameters left to regroup these 2. And so doing this, in this example, has reduced the number of calculations down from 2 to the 9 to about 2 to the 7. And again, this is a modest example, but in practice, this could be the difference between many orders of magnitude. Now, how does this process work where we regroup these pairwise? Well, as I mentioned earlier, the first thing we do is compute all the unique substates that each of these subgraphs can have. So instead of thinking of each of these graphs as a ZX diagram, think of it as a big list of the possible scalars it can be. So we've already reduced each of these to a big list. So A is actually just a list of 2 to the 4, 2 to the 2 numbers, B is 2 to the 2 numbers, and so forth. And so then when we come to regroup a pair, this is broadly the process we do. We look at the parameters involved in that pair. So in this case, we're regrouping big A and big B, which depends on little a, b, and c, these parameters. So we look at all the possible bit strings of a, b, and c, which are listed here. And in each case, we take the measured result for A 0, 0 and B 0, 0, and we multiply them together, and we work out that for each of the ABC. And then we look at all the cases where AC is 0, 0, and we sum them, and then AC is 0, 1, and so forth. And this gives us a big list for the possible unique states that AB could have. So that's the process for how we do this. And this just shows the unique states of A and the unique states of B. So in practice, well, the examples we've looked at have been very simple chains of subgraphs that are connected to each other, like linearly. But in practice, you can imagine that if we're using graph partitioning algorithms, we don't really need to go into the details of how these work. We can just treat it as a black box, which we can just get from the literature to optimally partition a graph. It might end up as something a bit more messy like this. And we're always cutting vertices rather than edges because that's more efficient. So we end up with a hypergraph. So this just shows you could have these different subgraphs connected to each other in this kind of fashion. And each of these subgraphs will just be storing as a big list of all the unique states. And how we want to notate this, So you can imagine this is what it would actually look like, but we want to annotate this in a nice, neat form. So we just do a hypergraph with a little number to say how many edges are connected between these two subgraphs. Okay, so all of this is packaged into a Python package, which again, I'll come back to later with a link if you're interested. And so how this works then is you would provide a ZX diagram in a reduced form, and you'd call this function partition. And this just uses some pre-existing algorithms from the literature to optimally partition, and it's a heuristic algorithm, but it's very efficient and effective. So in this case, we've taken this ZX diagram and it's optimally partitioned it into 7 parts, and it's determined the number of parts itself to be optimal as well. And each of these graphs depend on some number of the parameters involved in the number of cuts. So we represent this as a hypergraph. We pre-compute each of these graphs for the list of unique states it can have. And already we can see here that it's reduced the number of calculations involved in this small example by a small factor. And then we get onto the idea of regrouping them all pairwise. And we always do the cheapest pair. So that's the pair which collectively involve the fewest number of parameters, because then we have to iterate over fewer unique bit strings. So in this case, we want to regroup F and G together into FG, and then it says A and B is the next cheapest, and so it'll do that, and so on and so forth, until eventually it's fully regrouped. And so each of these, you'll remember, is a list of 2 to the n scalars, where n is the number of parameters involved. And so ultimately you'll end up with just one, which has no parameters, so it's just one single scalar, which is the actual final result. So again, in this example, we've gone from 2 to the 13.5 calculations down to 2 to the 7. And again, if this was a more realistic and larger example, this would be much more significant. And as well as, instead of optimizing just for the number of calculations, if we balance the speed of these calculations, then we can do some further optimizations there, but it's much simpler just to think of it in terms of the number of calculations for now. But what this translates to in practice in this example is 1.6 seconds down to about 3 milliseconds. Some more interesting examples. We have this graph here, which came from a larger ZX diagram with T count 100 and something, I guess, where this would have taken a matter of years. So we can calculate how long it's going to take based on how long the number of calculations, how long each calculation usually takes, and we know how many calculations we're going to have to do. So in this case, we calculate that the normal decomposition method would take a matter of years, whereas this method took under a second. And then here we have some more realistic examples from randomly generated graphs. So you can see they're not very pretty to look at, but you don't have to deal with that. The software will automatically figure everything out and just give you the final result. So for some benchmarking results to kind of see how effective this was in practice, we can see that this is the normal method without partitioning. So I generated a whole bunch of random Clifford T ZX diagrams of different depths and qubits. And a bit awkwardly, depth here just means the number of gates rather than the actual depth in the normal sense. So you can see that, oh, I should mention the scale first, actually. So this is a log scale of seconds, so log 2 of seconds. So 0 means 1 second, 6 is about 1 minute, 12 is about an hour, and then 16 is about 18 hours. So roughly speaking, anything in black is trivial to compute. It'll take less than a second. Anything in white is computationally infeasible. It's going to take a matter of days at least. And then the colored region in the middle, like the frontier, is the interesting region. This is where it's taking seconds or minutes or perhaps a few hours. So we want to see kind of where this lies, the balance between what is computationally feasible and what isn't. So this is the normal partitioning method. You can see very deep circuits are not very effective because depth here is just the number of gates. And if you have more gates, you have more T count. And the normal method depends pretty much only on T count. Whereas with our method, it's slightly shallower. So you can see now that this top right corner, the very deep circuits with lots of qubits, are now a lot more computable. So a specific example here is each of these are averaged over 10, but to look at a specific average for 1,000, depth 1,000 with 120 qubits, you can see previously this was taking 2 to the 25 seconds, which I guess is a matter of months, something like that. Whereas instead, the new method is taking 2 to the 5 seconds, which is like half a minute. Okay, and this is with fully random ZX diagrams, Clifford T ZX diagrams. But something else to consider is the spread of the C knots. So there's some papers that argue that, maybe just by intuition, this would make sense, that in realistic circuits, the C knots are unlikely to be spread completely randomly. They're more likely to be connected to nearby qubits. So with this in mind, we're going to run these experiments again, but this time when we generate the Clifford T ZX diagrams, the C knots are going to be more likely to connect to near neighbors. And this will be based on a normal distribution, normal function, with this parameter sigma, which is just the standard deviation or square root of the variance. And so what this determines basically is how likely it is to connect far away. So for instance, if we have sigma is 2, so that's this dark green line, then we're saying the probability that the qubit will connect, let's say 4 or 5 qubits away, so the source from the target is 5 qubits, is about 15% of the chance that it'll connect to its nearest qubit. And we can vary this sigma accordingly. And the extremes here are sigma equals 0 means that it always connects to its nearest neighbor, so either directly above or directly below qubit. And sigma is infinity just means it's equally likely to connect to any of the qubits, which is essentially what we did previously with this graph, where it's just a uniform distribution. So to look at a specific random example, we have, again, averaged over 10 examples, circuits of qubit 30 and depth 1,000. We see that when sigma is very low, the new method is much more effective by orders of magnitude versus just the normal approach. And this kind of makes sense because if you have CNOTs that connect nearby, are more likely to connect nearby and like 3, 4, or 5 qubits away rather than 10, 15 qubits away, then you can imagine it's naturally going to lend itself to graphs that are more partitionable because you just have to cut along these more local lines. And then as sigma is increased and it becomes a normal distribution eventually, then the new method is not very effective. And in fact, it appears to be much worse. But in fact, we can say that the k equals 1 partition, which just means don't partition at all, is a special case of this partitioning method. And since it is determined in the optimal k in advance, we can allow it to just make no cuts if it determines that it's best. So all of these, this red line should actually be capping at this blue. So we can actually say this is a more accurate graph of what we have, so that it never actually performs worse. But after a certain point, it's the same as just doing the normal decomposition, which in this case is at sigma of around 3.5. Okay, so for a broader class of experiments then, to repeat what we did previously with the heat map, and this is for sigma equals 2, so that'll be the green line here. So you can see it'll usually connect within about 6 or 7 qubits away, and it's unlikely to go further than that. Yeah, so here we see the frontier is drastically reduced, so we can suddenly compute lots of graphs that we couldn't compute before with this partitioning method. And this kind of speaks for itself, I hope. You can kind of see that in almost all, apart from the very extreme cases, we've managed to do significant improvements of many orders of magnitude. And this is where we see things that would have taken years to compute is now computable in milliseconds, just because we've reduced some massive T-count graph very efficiently with very few cuts into lots of smaller T-count graphs that happen to connect in very neat ways that we can regroup. Okay, and this is a broad idea of the paper, and this is kind of the results that we have presented in that. And now I'm going to talk about some future work which isn't in the paper, or at least it's alluded to in the paper, but there's no actual results yet for this, and this is something for later down the line.
I wonder if this is a good time to ask questions about the previous part, or
yeah, I mean, there's only a couple more slides left.
okay, I'll let you continue talking then.
Yeah, okay, and then we can come back. So this part is just to say how we can improve the partitionability, so we make it more likely for graphs to be able to partition efficiently. So you'll remember that the method we use to simplify the ZX diagrams is based on, well, largely these two rules, but other rules as well, just the pivoting and local complementation. And these are very effective for reducing the T count. But you'll notice that they both introduce a lot of edges. And if we have more edges, then it makes it harder to partition, generally speaking, because you need to make more cuts to try and partition the subgraphs. So something to consider is how we would balance reducing the T count, but without increasing the number of edges too much. So in certain cases, we might want to decide, do we want to apply this rule, or maybe do we want to apply it in reverse, going right to left, even if that means increasing the T count, but reducing the number of edges to make it more partitionable. So another example then would be the bialgebra rule. This is how it would normally be expressed left to right, but if you can imagine we have two subgraphs, one on either side, and we want to partition these, then you can see on the right example, if we say there are n edges on the left and n edges on the right, we would have to make, in this case, n cuts to separate these. Whereas on the left example, we don't have to cut it once. So with this in mind, it would make a lot of sense in many cases to be applying bialgebra rule in reverse to try and make it more partitionable. And then a similar example then, if these were all separate subgraphs and we wanted to disconnect them all, then instead of doing n cuts or m cuts, whichever smaller, which could be any number, we only have to make two cuts, and that completely separates all these subgraphs. So we could use some clever heuristics to try and determine when and where we should be doing this kind of thing. Or it actually lends itself quite well to reinforcement learning, where we know the action space is just the rewriting rules bidirectionally, and we can measure how partitionable a circuit is just based on, we can calculate, we can run the ZX partitioner and calculate how many calculations and approximate the runtime. And based on that, we can measure the partitionability. And so given those two things, we should be able to train a reinforcement learning model to try and figure out how to make these circuits more partitionable. And then lastly, one last method to consider is this idea that we can toggle the edge connectivity of any set of spiders, light-colored spiders that are connected with header mods. So if we look at any click, so in this case, we're looking at just these 4 green spiders, any non-edges with the hop rule, we can say are actually double header mod edges. And then we just apply local complementation in reverse and cut the new spider that appears. So for the cost of 1 cut, we can toggle the edge connectivity of any set of spiders. And why this is useful, if you've got, say, 5 subgraphs that are all connected just by this one point, then we can say here, we'll toggle the edge connectivity of alpha 1, 2, 3, 5. And we end up with this graph, and then we toggle the connectivity of alpha 3, 4, 5, and then we've completely disconnected these at the cost of 2 cuts. And in this case, it's easy to see by inspection what the most efficient way of cutting this is, and picking the sets in each case to toggle. But in larger scales, it's kind of harder to figure this out. So we want to use some kind of heuristics or reinforcement learning. Because if we picked all 5 of these and tried to toggle the edge connectivity that way, then that would have actually been less efficient than doing it in parts as we've done here. Yeah, so this is some future work to consider. If you're interested in seeing the paper or the code is up on GitHub, then you can find it in these two links. And I'm happy to take any questions.
Right. Thank you very much, Matthew. Very nice talk. Very cool results. I have loads of questions, but I'll give you other people an opportunity to ask their questions first. Is there anyone in the audience who would like to ask a question?
I've got a comment about this last thing about the bialgebras.
Yes.
Did you? Well, no, actually, it is a question, I guess. Did you think about using the cut rank for this? So at least for the 2, I wouldn't know how to do it with lots of G's, but at least for the 2 separate G's like that, you could compute the rank of the biadjacency matrix to get a transformation there.
Yeah, potentially. These are only kind of rough ideas. I haven't actually coded anything up or done any experiments for this. That's why it's in the future work. But yeah, potentially that could be something to try.
Yeah, so I know that this thing is something that Julian Kotze looked at in his master thesis. Like this idea of talking. I'm not sure if that's where you have the idea from, or if this sort of you did this independently.
Certainly this idea, I think, was mentioned
Yeah,
in Cody's thesis, where you can
yeah,
toggle the edge connectivity
yeah.
by reversing local commutation. Obviously, for my ends, it's for a specific purpose of trying to increase the partitionability, which is kind of inversely proportional to the number of edges, but
Yeah,
kind of
yeah.
depends on where those edges are.
So I know that Julian is now doing a PhD on graph theory at Princeton, and he told me he's still very interested in this question of like looking at simulability. So it might be worthwhile reaching out to him to see if he has any more ideas about.
Yeah, I think I saw your paper with him was recently published, right?
Yes, yeah, after a very long period, but yeah. Any other questions for Matthew? Okay. Oh, Alex, yeah.
Yeah, I guess since you mentioned reinforcement learning, do you have an intuition yet of what sort of reward function you would use in order to train the model?
I guess it would essentially be the partitionability, right? Which is so if we actually run the ZX partitioner, we can, and this is very quick to run because we don't actually have to calculate the final result, but we can calculate how long it would take to get the final result. And so based on that, we can have a sense of how efficient this is to partition. So that's why in this graph, where are we? In the heat map, you see these numbers go up to like months and years. Obviously, I didn't wait months and years for these experiments to run. The point is that we can calculate how long it's going to take to run based on the number of calculations we know it's going to take and how long each of those calculations on average does take. So we can use this kind of thing to predict how long it's going to take and use that to say how partitionable it is. And obviously, if this number is smaller, then it's more efficient. And so we want to try and use that to optimize for, if that makes sense.
Yeah, cool, thanks.
Have you looked at any operationally meaningful circuits with magic?
Could you say that again, sorry?
Have you looked into any operationally meaningful circuits with magic in it or teak?
Oh, no, this has just been on random circuits, uniformly random, and then the distribution random. It might be worth looking into real world circuits and see how this kind of relates to those. Hopefully, it'll be something more akin to these lower sigma circuits because, as some of the papers have suggested, these are more realistic.
Thank you.
So I was wondering, because a lot of the work seems to be doing by this partition function that you said was sort of like a well-known thing from literature. But it wasn't super clear to me what this thing is actually doing. Like, what is the graph theoretic definition of a partition? What is the metric it is minimizing? And like, what is this thing internally doing, and how expensive is that?
The partitioning step specifically, or in general?
Yeah, like you have this like magic function that says partition this graph for me. Like, well, what is that actually doing?
Yeah. Yeah, this one here. Wait. Yeah, this one.
Yeah.
So this one essentially just uses existing graph partitioning functions, which would kind of be a whole talk in itself. But broadly, we can just consider it a black box where you just provide a graph, in our case, a ZX diagram, and it finds an optimal partition into k segments. There's a few modifications that I've made, which is that instead of having to specify what k you want to partition it into, I let it decide what the optimal k is. So it tries k equals 1, and then k equals 2, k equals 3, and it keeps going until the answer becomes worse. And so say you do k equals 7, and this is very good, and then k equals 8 becomes worse, then it knows k equals 7 is the best answer, or likely to be the best answer. And it's very heuristic, so you're not going to get an optimal solution. But this step is just to partition it into several subgraphs, and there's nothing particularly novel in this. This is just kind of borrowing from the literature.
And just to be clear, a partition is like a vertex partition. So like I group the vertices into separate subsets that like disjointed together from the whole graph, and I ignore all the edges that are in between vertices.
I think the actual problem in the literature is called the minimum balanced k-cut problem. So you give it a graph and some kind of k to partition it into some number of partitions you want to make. And the idea is to separate into roughly equal-sized subgraphs that are connected with the fewest number of edges, which is exactly what we want to do here in our case. Yeah.
And then your cost is something like 2 to the power of k times the largest partition element, because that's sort of roughly the cost of your executing this thing, right?
The cost of the partitioning step.
Yeah, it's just like if you have like k different graphs, they have like a 2 to the k, but then also it's multiplied by the cost of the most expensive graph, I guess. So would that be
as
sort
in
of
the
like
next step.
yeah.
Yeah, as in the number of calculations we have to do. Yeah, and that's kind of where we derive these numbers from, because we can calculate how many calculations we're going to have to make.
Yeah.
But to get to the point where we have our subgraphs, and then we represent this in terms of how they're connected to each other as a hypergraph, to get to this point, this is very efficient. This is just the heuristic partitioning algorithm. It might be like 2 to the n for n vertices, something like that, which, n squared, which obviously compared to like 2 to the n for the number of t-gates and so on is negligible. And once we have this hypergraph, we can calculate how long it would take to reduce it without having to actually reduce it, which makes it very helpful for using it as, for instance, in reinforcement learning to give it a reward function.
Yeah. So are you essentially doing like a hypergraph tensor network contraction on this thing now, like this sort of thing that Johnny Gray does?
It's very similar in terms of like the graphs that it's effective on. So if I run to the paper, can you still see my screen?
Yeah.
Yeah. So this is something I thought about as well, and I mentioned in an appendix somewhere. Yeah, because it does appear to be effective in the same cases that tensor contraction is effective, but it's not always the case. So if we look at graphs like this, where we have, imagine basically we have a bunch of circuits or ZX diagrams that are internally very dense in terms of the connectivity between them. So it has lots of edges connecting. But between these separate subgraphs, there aren't many edges. Then this would be quite poor for the tensor network approach, because if each of these individually is really interconnected, then that means the whole thing becomes treated that way. So it doesn't reduce very well. But if each of these individually is very effective for stabilizer decomposition, then we essentially get the best of both worlds. So we're doing stabilizer decomposition over each of the subgraphs, but a tensor contraction type approach between them. And so we found a bunch of examples of circuits like this, just randomly generated, where the tensor network approach just wouldn't work because it would just try to allocate hundreds of gigabytes and it would fail. Whereas this method would be able to do it using just a few gigabytes and just a few milliseconds.
But then the last step, like where you now have this like reduced hypergraph tensor, then you just use, like I say just, but then you use like a sort of like a heuristic algorithm for saying in which order should I contract this to minimize the cost, which is like and that would be like the stuff that was done by like by this k-hypar kind of library.
So when we regroup the pairs, we said that in this case, for instance, A and B depend on 3 of these parameters. So it would take 2 to the 3 calculations. So whenever we're regrouping pairs, we want to find pairs that between them have the fewest number of parameters. So when we did this over here, we saw that F and G depend on however many that is, 4 parameters. So that would be the cheapest pair to contract. So we contract those 2. And then that's just the heuristic we use, always contracting the cheapest pair based on how many parameters they have between them, until eventually it's fully contracted.
So you mentioned that these local complementation and the pivoting, they might introduce a lot of edges. So are you implying that you're not using these when you're thinking about this? So you have like your circuit and you only do like spider fusion or something before you give it to...
Currently, this is just using the normal ZX.reduce function, which does use this, obviously. And this is just ideas for future work where maybe we don't want to be using these so much. or we want to be a bit more discriminatory about when and where we are using them, because it might be a lot more efficient in a lot of cases to not reduce the t-count so much if it means keeping a fewer number of edges and making it more partitionable. It's about finding this balance. But all of that is for future work. For the current methods, with the results I've shown, that's just been reducing the graph with a normal ZX, which does introduce a lot of edges. So I think there's a lot of room for improvement.
Yeah. Yeah, so yeah, that is kind of surprising that when you have this locality on the C naught, that still gives you these better results. Because I would have expected these local complementation and pivoting to sort of get like scramble this locality and make your graph much more densely connected.
Yeah, I guess it preserves it in some capacity. It's kind of hard to analyze that. But yeah, the results kind of bear it out that when it is a lot more local, the performance is a lot better.
So on this graph, I didn't fully understand what you meant by, oh, it could just choose k equals 1 and therefore it's equal to no partitioning, because the graph, yeah, previously it went above the naive one, but you were already using the heuristic of starting with k equals 1 and going to k equals 2 and picking the one that's the least expensive. So
Yeah,
why wasn't it doing that?
the only difference in these two graphs is that this one, the partitioner methods always make at least one partition.
Okay.
And I'm just kind of showing it because it's an interesting graph, I think. But this one is more reasonable because this just includes the k equals 1 case. So if it decides that any amount of partitioning gives worse results, then just don't do any partitioning, which is why it caps at the blue line.
Nice. Okay, I think that might be it for my barrage of questions. Are there any other questions in the audience? So actually, I thought that Alex Cosriel and Richie, like they had a paper on doing like sort of machine learning approaches for this kind of. Maybe
I was on that as well. Yeah.
You're also that. Okay, yeah.
Yeah. Yeah, I mean,
Yeah.
this
So I guess
is
I'm wondering, like, what's the connection, if any?
well, it was kind of an afterthought, the reinforcement learning stuff on this paper. It kind of came from having done that other paper that I kind of occurred to me that it could be very applicable here. So maybe, I don't know, if Alex, if you think this makes sense to use reinforcement learning here.
It seems like it would intuitively. I think that what's nice is that a lot of what we did in the previous work would easily translate over to this. So it wouldn't be too much of a time investment to at least try. So yeah, we should talk about it, Matthew.
Yeah, sounds good. I mean, I think it lends itself well from the fact that this partitionability factor is measurable and we know the action space, which is kind of all we need, I think, really, to know how to get started.
Yep.